Hello, everyone, and thank you very much for attending my presentation. Let's get on with it. So, picture we want to go back to the moon. And this time we actually want to build a base. But for that, we're going to need help from potentially robots that are going to help us build those facilities that we want. And also maybe explore a bit. Now, robots comprise motors, mechanisms, sensors, and also control and communications devices. And each of these typically require specific equipment and facilities to be built. And it is not really feasible to think of having each of these facilities built on the moon before we even have the workforce that is going to help us build them. And arguably, we could just bring the robots from Earth and together with them all the parts that we need. And that can be a good start, but it won't be feasible in the long term as we need to bring in more spare parts and additional weight that takes a lot of cost to bring from Earth into space. So also not a very sustainable approach. But what if we were able to fabricate all of these different components with a single manufacturing equipment in a single facility? Well, then we would need that manufacturing technology to be versatile, to be able to fabricate many different things. Should be able to handle multiple materials, and it should also be low waste, because any waste that we produce in space is something that we've had to bring from Earth at a pretty big cost. So these are requirements for that technology. And ideally, it will also be cost efficient and fast and easy to operate. Well, it turns out that these features are some of the virtues of additive manufacturing, and additive manufacturing of the devices that I just described is basically additive manufacturing of electrical machines and electronic devices, which coincidentally is the title of my thesis. Now, I've described this technology for the purpose of building robots on the moon, but if we have that manufacturing technology that allows us to build all of these different components with a single equipment, then that would also be applicable in universities, in businesses, big and small, in schools, in developing countries, even at home, so virtually by anyone and anywhere. Right, so let's get on with this. This is the outline that I'm going to follow. I'm first going to talk about that technology that we propose that is able to fabricate all of these different devices. And then I'm going to talk about the different applications of that technology, meaning those different devices that we can actually fabricate with this technology. Right. So what is the technology that we think that can enable this multi-purpose fabrication? We think that one that can do this is material extrusion. And material extrusion is an additive manufacturing technology that takes material, puts it through an extruder, and it pushes it through, normally heats it up and melts it, and then pushes it through a nozzle, building parts from the ground up. Now, this technology is characterized by being simple, affordable, and accessible. It's the additive manufacturing technology that everyone thinks of when you initially talk to them about 3D printing. It's the one that is most widespread around the world. And it is modular. Why is that specifically important? Well, because this is an extrusion module, and there's nothing stopping us from replicating it and putting several of them in parallel. And with this, by being able to handle different materials at the same time, we turn material extrusion into multi-material extrusion. And there are companies that have been working on this and are commercializing machines that are capable of multi-material extrusion. For example, here is a Maker Gear M3ID, which can simultaneously print from 2 different filaments. And this is an E3D motion system and tool changer. This particular machine can use up to 4 different tools, which enables it to use 4 different materials in the same print job. And it is very customizable, which is good because, well, on the one hand, it takes a lot of work to customize it and make it function, but it has a lot of potential for the research that we can do with it. And right, so these are the machines that I have worked with the most during my PhD, and I will come back to mostly the tool changer one. Now, so we can print with multiple materials. Which materials do we actually want to use? Well, typically feedstock for material extrusion is a polymer-based filament. For example, PLA or polylactic acid is a very common one. And its advantages are that they are easy to use, easy to acquire, and they can contain functional infill. Now, this is particularly important because many applications that are out there for multi-material extrusion usually focus on printing with the same plastic but with different colors, which looks pretty nice, but there's a lot more that we can do with it. If we add functional particles of functional materials into these filaments, we can make functional filaments that we can print with. For example, there's this conductive filament commercially available that is PLA doped with copper particles. And there's also a magnetic filament that is, again, PLA doped with iron particles. So embedding functional materials into these filaments allows us to have performing materials. Now, there is an issue with this, which is that the infill percentage that we can embed into these filaments is limited. And it is limited because if we go past that percentage, then the filament becomes unprintable. So we can't really use it. And that means that there is a limit to the functionality that we can achieve with these materials. But there are alternatives to these filaments. For example, there's ink or paste, and there are also pellets. Now, these materials are not necessarily meant for material extrusion additive manufacturing. In particular, this one, the ink is meant for screen printing or other electronics manufacturing, and the pellets one is meant for injection molding, so a more traditional manufacturing method. But they, if we are able to adapt our 3D printing system and make it able to use these materials, then we will be able to access much higher performances. And to illustrate that, here's a comparison of the electrical conductivity, which we would hope for to have the highest value, between the conductive filament that I mentioned in the previous slide and this silver ink. And as you can see, there is a 1,000 times difference between their performance. So a pretty big gap. And if we look at this material, which is magnetic, and we compare its relative magnetic permeability, we see that between the filament and these pellets, there is a 10 times gap in performance. Now, let me mention that this material is soft magnetic, so it's not the one that you would want to use for making a permanent magnet, but instead the one that you would want to use to make magnetic cores. So not generating magnetic fields, but instead strengthening them and channeling them. And the figure of merit to look, an important figure of merit to look in those materials is the magnetic permeability. So if we are able to print with these non-conventional materials, at least when we're talking about 3D printing, then we would be able to access much higher performing materials. And how do we do that? Well, we have to customize this printer that I mentioned earlier, the tool changer. And the way we did that was we kept one filament extruder because there are still filaments that we are interested in using. And we swapped the rest, one for a pellet extruder and another one for an ink extruder. This is the final lineup that we have in this printer. So we have an ink extruder, a pellet extruder, a filament extruder, and a heater for curing the ink that comes out of the ink extruder. And with this, we are able to access the 3D printing of high performance materials. So what do we do with this? Well, that's what I'm going to talk about now. The different applications that we were able, the different devices that we were able to fabricate with this technology, starting with motors. So motors are typically comprise magnetic cores and solenoids, and they can also have permanent magnets. I'll mention that later. Magnetic cores are meant to strengthen magnetic fields, while solenoids are the ones responsible for generating those magnetic fields. And I'm going to start looking into the magnetic cores. So by introducing the pellet extruder, we became able to fabricate these cores from a higher performing material. And we characterized them in several ways and found that we are able to reach this relative permeability of about 30. Now, is that good? Well, if we compare it to other 3D printed cores, that don't rely on temperature post-processing, then we can see that we are outperforming those by pretty significantly. But there are other ways to get higher permeability, mostly by means of post-processing at around 1,000 degrees. So higher permeabilities are possible from 3D printed cores. The thing is, we don't really want to do that because if we keep in mind that we want to keep this technology compatible with multi-material fabrication, and in particular, we might want to keep it compatible with polymers, then we can't treat it at 1,000 degrees because any polymers that we put through that temperature are going to burn. We did a bit additional characterization with help from Dr. Steven Nagel from the Rogers lab. And we were able to get this beautiful pH curve. And from it, we found some interesting data about our cores, including the core losses, which compare very well to other 3D printed cores. And we were also able to see that we can modulate the performance of these cores by tuning the printing parameters. So for example, this extrusion multiplier parameter, which basically translates to density, we can tune it in the printing software. And with that, we can access different values of permeability with these cores. So now we are looking into different possible applications for these devices, which include multi-permeability cores and also open loop energy harvesting, which we are working on in collaboration with our colleagues at the Imperial College London. Right, so that's it about the cores. Now let's talk about solenoids, which, as I mentioned, are the responsible for generating the magnetic fields that we want to use. And ideally, we want those magnetic fields to be as strong as possible. So 3D printing can practically make any shape, but it's also good if we help it by coming up with a 3D printing friendly design. And so that's what we did. And we came up with this design, which is a stack of conductive spirals alternating with insulation layers. And there we go. And we did a few different iterations as we became able to use higher performing materials, mostly with, well, always with the objective in mind of generating higher, stronger magnetic fields. In the first iteration, we used the copper field PLA filament, which I mentioned earlier, and no material for the core, or an air core. In the second iteration, we used the same conductive material, but we introduced a magnetic core using the iron field PLA filament that I also introduced earlier. In the next iteration, we swapped that filament for the higher performing pellets-based material that we printed the cores from. And later we introduced silver ink. So we swapped the conductive filament for silver ink, and we printed those both with an air core and with a magnetic core. And we looked at this, we imaged them in several ways, including CT scan or X-rays. And we did see that we noticed that the monolithically 3D printed cores that we were fabricating were not turning out fully dense, which is a problem because we probably wouldn't get the performance that we were expecting from this. So we came up with an alternative fabrication process to check this, in which we fabricate a bar of this magnetic material from which we can break pieces and make them into cores that we can then insert into 3D printed solenoids. And so the way we characterize these solenoids was by measuring the magnetic fields that they generate. This is the experimental setup, which has a magnetic shield and a 3D printed support structure that holds the probe and the sample in place. Now, we started with the first iteration of the solenoids that we made, which have the copper field PLA filament as conductive material and no core. And we were able to print them with multiple numbers of layers. Now, the first thing we did was we estimated the magnetic fields that we were expecting to see from these generated by these solenoids using this equation that computes the magnetic field generated by a loop of current along its axis at a certain distance. So we approximated all of the loops in these spirals by circles, and we added up all of their contributions. And these are the estimates that we got from that calculation. And then these are the measurements that we took. So as you can see, they are very much in very good agreement. And they're also consistent in the sense that, so we're getting what we would expect. Actually, we get magnetic fields that rise linearly with the injected current, and they also rise sublinearly with the number of layers. This is also to be expected because as we add more layers, they contribute to the magnetic field, but they are farther away from the measurement point, so they don't contribute as much. And so then we started adding magnetic cores, first with the iron filled PLA filament, which gave us about a 6% increase in magnetic field. And then with the FESI-AL filled nylon, so the one coming from pellets, both in its monolithic implementation, which gave us about a 25% increase, and in its inserted implementation, which gave us almost an 80% increase. So there is a pretty nice noticeable improvement, and so this it demonstrates that there is a lot of potential in these core materials and including these cores in the solenoids. And then after that, we introduced the silver material, silver ink. And as you can see, the big plot that was here occupying all of the slide just became quite small. That is because it has to make room for the much higher performance that we were able to get from the silver ink-based solenoids. And both with an air core and even better with a magnetic core. And now this improvement in magnetic field is mostly by virtue of being able to carry higher currents. And so the limitation for the magnetic fields that we are able to get is mostly due to the resistance of these devices, because the resistivity of the materials is quite high. When we put a current through them, they heat up, and at some point they start to deteriorate. So that limits how much current we can put through and how much magnetic field we can get out of them. In the case of the silver ink-based solenoids, the resistivity is much lower, so we are able to put more current through them and get higher magnetic fields. But they're still limited by the same phenomenon. And so we get 20 Gauss. How much is that? Is that good? Is that bad? Well, to put it into perspective, the magnetic field of Earth measured at its surface is about 0.5 Gauss. And we are getting about 20 Gauss. And the magnetic field of a refrigerator magnet is about 50 Gauss. So we're not making the strongest electromagnets ever, but we are definitely within the useful range of magnetic fields. And to demonstrate that, we implemented two different applications, one as a sensor. So if we place one of these solenoids in the vicinity of a rapidly changing magnetic field, we are able to pick up a varying voltage that effectively monitors the change in the magnetic field. So we have a magnetic sensor. And then, well, I promised a motor, so movement, actuation, and we also managed to do that. And for that, we combined other different materials. We used the flexible material that Dr. Hanju Lee and Zoe have been working on in our lab for the past years, and also a hard magnetic material that also Zoe has been working on. Now, this is the material that you would want to use to make a permanent magnet. You can print it, you magnetize it, and there you have it, a permanent magnet. So we put this together to get this sort of two-dimensional spring or membrane with a magnet at its center. And then if we put that on top of one of our solenoids, we get a linear motor. And so by biasing this, by placing a voltage across the solenoid, we are able to generate attraction and repulsion forces on the magnets. And we characterize this by changing the bias voltage. And we were able to see that it's mostly linear, except at its edges where it seems like it's starting to saturate, which is something that we would expect from this type of device as the deformation becomes of the order of the width of the beams. And we also excited this by introducing a sinusoidal signal. And with that, we made it oscillate. And by measuring the amplitude of that oscillation, we were able to characterize the frequency response of this device, and including figuring out the resonant frequency of this device, at which it oscillates a lot more than at any other frequency. And from that, we were able to do a little further characterization, for example, finding the spring constant of this particular device at 75.2 newtons per meter. And this type of data will help us inform future designs of this type of device. And this is the first fully 3D printed motor, so a pretty exciting achievement. And the next step would probably be turning this linear motor into a rotary motor. We didn't get quite there yet, but to convince myself that we could actually do it, I also 3D printed these bearings with the same machine, same material extrusion 3D printer. And as you can see, they turn quite smoothly. So I'm confident that we can put all of this together and come up with a rotary motor too. And that is all about the motors. Now I'm going to talk about logic and control devices. So the idea here was to make devices that allow us to control and process information with the same technology that we just used to print a motor. And for that, we focused on the copper PLA field, copper field PLA filament that I mentioned earlier, that doesn't perform as well as the silver ink, doesn't have such a good conductivity, even though it is still the most conductive filament available on the market. And it turns out, or we found that it exhibits a behavior called polymeric positive temperature coefficient that we can leverage to make these logic devices. And so this phenomenon is as follows. So if we add conductive particles to a polymer, or to some polymers, they form conductive chains that effectively create a conductive path, making the whole polymer slightly conductive. Now, if we heat it up, then it's going to reach a point called the glass transition temperature, at which the polymer becomes much more susceptible to thermal expansion. And by means of that expansion, the conductive chains break, bringing the resistance of this device, making it rise by orders of magnitude. Now, luckily for us, this is a reversible process. So if we let it cool down, the conductive chains reestablish themselves, and we are back to its. It goes back to its original resistance. And so we were able to find that this material exhibits that behavior. We were able to characterize it. This is the type of sample that we used for that. And we saw that if we apply a high enough current, in this case 120 milliamps, soon after a little bit after applying that current, the resistance of this trace spikes by 2 orders of magnitude, which is very significant. We were also able to see that if we turn the current off and we let the device cool down, it eventually, after a while, recovers its original order of magnitude of resistance. So it is reversible. And we were also able to see that we can do this over and over, and the behavior repeats itself. We did this, I think, up to 4,000 cycles, and we found no sign of deterioration. So a pretty consistent phenomenon. And another feature that is interesting about this phenomenon is that it is localized. So to illustrate that, we have this sample here with 3 different segments. And we saw that the phenomenon only occurs in the segment that concentrates the highest current density. So the one with the smallest section. And so with that, we can anticipate that the phenomenon is going to happen here in the BC segment. And so if we look at thermal images of this of this sample, while applying a low current, we see that not much is happening. But when we apply a higher current, we see that indeed it is that segment, the one that heats up excessively, while the others sort of remain undisturbed. And if we look at the resistance, the evolution of the resistance of each of those segments, we also see that is indeed what is happening. We see that the resistance in the segment AB and that of the segment CD, they pretty much remain undisturbed throughout the whole experiment, while the resistance of the segment BC spikes soon after we apply the high current. And this material, we tested a few different materials, conductive materials for 3D printing, and we found that this is the only one that exhibits that behavior. So it is pretty special. And so what do we do with this? Well, we were able to come up with a 3D printed switch. And the way we did that was we basically designed two intersecting conductive paths. One from A to B that we used as the power path, and another one C to D, which we call the control path. And the way this works is if there is no bias applied to the control path, then the power path allows the nominal flow of current. But if we apply high enough voltage across the control path, it triggers this spike in resistivity phenomenon at the intersection of both paths, effectively cutting the current through the power path. And we can actually see that through measurements. Here we see that when we apply a voltage to the control path, we can measure a spike in resistivity happening in the power path. So we are effectively capable of modulating resistance electrically. And this, well, completely different physics and very different performance, but this is what a transistor does too. So we can use this in similar ways to how we use transistors. And this is the symbol that I came up with to keep track of this device in the schematics. And one possible use for this is controlling a motor. So if, for example, we have this switch up here and the motor down here, and we are feeding it from a voltage source, if we don't apply any control signal, then the motor is going to spin normally. But as soon as we apply high enough voltage across the switch, the path is going to break and we're going to stop the motor. So we can control the motor with this 3D printed switch. And if we combine it with other electronic components, such as resistors, we can 3D print integrated circuits. And we demonstrated that with different logic gates. For example, this is the schematic of a NOT gate, and this is the 3D printed device. This is the input that we applied, and here is the output. We would expect the output to be the inverse of the input. And here the ideal output is in green, and the measured output is in blue. And we can see that it pretty much follows the ideal output quite consistently. And we also implemented an OR gate with this schematic. This is the 3D printed device. These are the inputs, which alternate high and low signals. And this is the output. In this case, we would expect it to be high whenever any of the inputs is high. And again, that is sort of what we see in the measured output with some deviations. And lastly, we also implemented an AND gate with that schematic, this printed device, these inputs, which again alternate high and low signals. And in this case, we expect the output to be high only when both inputs are high. And that is basically what we see. We do see, especially here, that there are some disturbances in the output. And these are mostly caused by the fact that we are leveraging a thermal phenomenon, which has very slow dynamics. So some of the inputs are turning on and off faster than the circuit can actually recover from the heat. So that's why we are seeing these spikes here. And so we were able to fully 3D print logic gates via material extrusion, which is also a first. And again, this is the same technology that we've used to print the motor. So it's all kind of coming together. And now, so I've talked about leveraging one thermal mechanism of this material. Now I'm going to talk about leveraging another thermal behavior, quite straightforward one actually, for microfluidics. And that phenomenon is simply that a resistor heats up. So we can print a resistor from this material, and if we put current through it, it's going to heat up. And we figured that we can combine this with microfluidics. Microfluidics have many different applications. They can be used for chemical reactors, for incubation, many different things. And many of those applications require temperature regulation. Now, material extrusion is also capable of fabricating microfluidic devices. And we came up with the idea of combining those microfluidics with resistors to integrate heating into the same device. There are ways of doing that, of integrating heating into microfluidic devices, but they usually rely on clean room processes, which are much more expensive and take much longer than what we are suggesting here. And so what we did, pretty straightforward, we put one thing on top of the other. We printed a resistor and we printed a microfluidic structure on top of it. And with this very simple proof of concept implementation, we were able to measure, we put a fluid from inlet to outlet of the microfluidic structure while exciting the resistor at a DC voltage. And we were able to measure a 4 degrees Celsius increase in temperature of the fluid from inlet to outlet in this particular experiment. So it works. And the most interesting thing about this is that it is extremely customizable. So with 3D printing, we can make pretty much any shape for the channel that we want. There is a limit to how small we can make it, but we can make any type of shape. And not only that, we can also make any shape for the resistor. So by simply changing the design of the resistor, we are able to produce different temperature profiles. For example, with this shape, we're able to produce a sawtooth-like sort of heating profile. And of course, the temperatures that we reach vary depending on the current that we apply. So what we've done this is we've come up with a way to create versatile and inexpensive self-heating microfluidics. And next, I'm going to talk about the last 2 projects that I'm going to talk about. I had the great pleasure of working on them in collaboration with Professors Neus Vidal and José María López Villegas from the University of Barcelona. The first one being about inductors, planar inductors in particular. Now, I've already talked about planar inductors. I've used them to make those solenoids. The solenoids are basically stacks of planar inductors. And as I mentioned earlier, we have the issue that the magnetic fields that we can generate are limited because of the temperature that these solenoids reach because of their resistance. So if we were able to lower the resistance, we should be able to reach higher magnetic fields. Now, a possible way to lower the resistance of a planar inductor is to make their traces wider. That would definitely give us lower resistances, but we would also generate lower magnetic fields because we are losing compactness. And if we look at RF applications, we would also increase the magnetically induced losses. We would reduce the self-resonant frequency, which is basically the highest frequency at which the device is useful. And of course, we would increase the device footprint, which when we are talking about electronics is something that we usually prefer to avoid. So the question is, well, there's a trade-off here. The question is, can we somehow balance this? Can we get the best of both worlds of thin and thick traces? And the answer is yes, we can just combine them. We can use both thin and thick traces by having a variable width. This is actually an optimization strategy that is used in RF applications to optimize performance around a specific frequency. And what we were wondering here is, can we use this in DC to improve the magnetic fields that we are getting, and what happens all the way from DC to RF. And so for that, we fabricated these inductors, again, with the help from the Rogers lab. And we fabricated 2 sets, each set having the same nominal inductance. And in each set, there's 2 inductors of constant width, one thick and one thin, and one variable width inductor. And so looking at their performance in DC, we measure the magnetic fields that they generate. And well, if we apply the same injected current, there's no question that the most compact one is going to generate the highest magnetic fields. But it's also going to be the one that heats up the most because of its higher resistance. Now, if we apply the same bias voltage rather than injected current, the resistance comes into play. And we're actually able to see that trade-off. And we found that it is the variable inductor and the variable width inductors are actually the ones that generate the highest magnetic fields. So pretty exciting. And this means that we can actually implement this, take it to our 3D printed solenoids and potentially improve their performance by means of leveraging this, this behavior. And when looking at the RF performance, we focused on the quality factor as a metric, which basically is the ratio of the energy stored in the magnetic field over the resistance or the resistive losses of the devices. And we were very happy to see that the quality factor of the variable width inductors basically envelopes those of the constant width inductors. So we are effectively getting the best of both worlds. And so with this, we have come up with a generalized way to optimize planar inductors for DC all the way to RF. And now the last project that I'm going to talk about is, right, so up until now I've talked about 3D printed electronics, and you could see that they were kind of big, a big scale, millimeters to centimeters. But when we are fabricating electronics, it's always good to try to think about how to make them smaller. And that is where this 2-photon polymerization, or TPP, comes in. So a bit of an overview of what 2-photon polymerization is. First, polymerization is a process by which many monomers come together to form a polymer. And it sometimes comes with an associated change of phase, which can be from liquid to solid. This is what many additive manufacturing technologies take advantage of. We normally start with a liquid resin and we end up with a solid part. And now photopolymerization is a particular type of polymerization where the phenomenon is triggered by light. So wherever we shine light, we trigger the polymerization process. And 2-photon polymerization is a particular type of photopolymerization where we use a tightly focused laser to trigger the polymerization only in the space where 2 photons interact. Now you can imagine that the space where 2 photons meet is very small. So we are effectively triggering this polymerization process in a very, very small space. And that makes TPP an ultra high precision additive manufacturing technology. And the particular printer that we used in this work is manufactured by UpNano, and it's available as a shared instrument over at MIT Nano. And we've used it with the help of Adam and Bin. And right, so now can we use this for making electronics? Well, for that we need to somehow throw metal into the equation. One way to do that is through multi-material TPP, which is possible, but extremely complex. So the alternative way that we looked into is combining TPP with a coating process. The particular strategy that we used is electroless plating, which is a chemical process for the deposition of metal on a surface. Basically, we start with this polymer part, and we end up with the same part covered in metal. Now, usually there is an intermediate step that is basically a surface conditioning operation. In this case, for example, we simply sandpaper the sample to give it some roughness. It can also be done chemically. There's other possible processes. And what we wondered was, can we substitute that step with two-photon polymerization? Because if what we need is certain surface roughness, then thanks to the resolution of TPP, we can actually just print that roughness on the part. So that's what this project is about, and it was actually started by Dr. Nick Lewinsky, by the way, back when he was in our lab, and we have given it a pretty big push. And so here's the process that we came up with. So we start with surface roughness design by first designing a surface texture element. We replicate it over a patch, and then we place those patches on the samples that we want to fabricate. Then we can print those samples and put them through the metallization process. In particular, we use nickel room temperature metallization, which consists of a series of sequential baths to end up with a metallized part. And now, so it works, but how did we actually make it work? Well, the first question is what does the surface have to look like? Because there's an infinite design space for the roughness that you can place on a surface. So to answer that question, we started working with triangular prisms, and we varied the parameters that define the different textures that you can generate with these patterns. And we placed all those different textures on a sample, printed it, and put it through the metallization process. And after doing that, we saw that not everything goes. So some patterns do catalyze metallization and some don't. So from this, we were able to find approximate thresholds for those parameters for where the metallization is successful and where it isn't. And we also tried different geometries. So not only triangular prisms, but also square ones, cylinders, star-shaped, triangular holes, pyramids, sand clock structures, and even randomly generated peaks and valleys. And what we saw from this is that, again, not everything works, but many do. The surprise was basically that the holes do not work, and the randomly generated patterns also do not work. But all other textures that were defined basically by a by a flat surface with high aspect ratio structures coming out of it, those do work. And so we did a bit of characterization on these devices by snapping them and looking at them with a microscope. So by doing that, we were able to see that the metallization, the metallic layer, is basically deposited on the flat surface and a bit on the sides of the pillars. Like this, we were able to measure the thickness of that metallic layer, and combining that with sheet resistance measurements that we took, we were able to see that the resistivity of these layers is at about 6 × 10⁻⁷ ohms meter, which is very similar to what we were seeing from the silver ink that I mentioned earlier, so pretty competitive. And with this method, we were able to fabricate complex three-dimensional structures with selectively metallized parts. And we even had the time to play around a little. And so what we came up with, what we propose here, is a technology able to fabricate finely featured three-dimensional devices with selectively conductivity in selective areas. And with that, I am going to finish the presentation by going back to our lunar robot. Like I said, it's gonna need motors, mechanisms, sensors, control, and communications. We sort of went over a bit of all of those. I didn't mention that, well, these spiral planar inductors can be used as antennas, so there we go. And we were able to fabricate all of this with the same single manufacturing technology, which is material extrusion. And on the way to figuring this out, we also found a few other cool results. So in the end, the robot is happy, I am happy, and I'm gonna take a minute to do some acknowledgements. Well, first to Luis, my advisor, for advising me throughout the PhD, and to my committee, Professors Akinwande and Lang, for their time and very on-point counsel. And then I also wish to thank the La Caixa Foundation and Empirico for funding my PhD. Also the extended MTL and RLE, EECS, and the wider MIT community. And I would also like to mention the professors that I had the privilege of learning from. And I would like to extend that also to the academic institutions that I had, that I attended before this, that led me to being here. And finally, on a more personal note, I would like to thank the lab members, past and present, for great times, and my family, which is always there, near and also near. Spain at MIT has brought a very homey feeling to MIT. Friends, old friends that are still there all over the world, and also new friends that I had the great pleasure of making along the way. And lastly, the best combination ever, which is friends and sailing, which has kept me afloat throughout my PhD. And with that, I would like to conclude the presentation, and I'm happy to take questions.